Cobol bites.
Hey, I resemble that remark.
What? No, it means little bites of Cobol.
Oh, why didn't you say so?
Today, Cobbie the Cobol Dinosaur wants to know, how type-safe is Cobol? By chance, while I was looking for definitions of types and type systems, I came across a site called The Valuable Dev by Matthew... Well, his name is on the slide. I won't try to pronounce it. I know my limitations. Well, some of them anyway. Matthew has a page about type systems, and it starts with the words on the slide. There are several reasons I like this opening. First, my name is Dave. Second, I like Cobol. Third, I write Cobol like a proper noun instead of an acronym because I think it's become so commonly used that it's an anacronym. That is, a word that used to be an acronym and is now a word. Fourth, it may well be that your next microservice invokes a Cobol program at some point in the course of a transaction, depending on what APIs it calls. Somewhere back in the back end of things, the transaction might be processed in part by a Cobol program. Fifth, I was just thinking about type systems. The only funny thing is the idea that Cobol has a strong type system. That turns out to be Cobbie's question today. To answer that question, we first have to understand what a type is. Here's a definition from Wikipedia. That definition is pretty broad. What do they mean by how the programmer intends to use the data? Will the programmer use the data in a sandwich? To level an uneven table? To scrape old paint off a barn? No, it just means what kind of data it is. Like, is it a chunk of text? Is it a number? Is it a date? Does it represent a domain concept, like a street address or a vehicle identification number? So it isn't that complicated. Some people like to say things in a complicated way. Examples are easier. Here are some. You might notice the names of the variables in these examples say they are one type, but they aren't. The names don't matter. The variables that are assigned the number 15 are numerical types, regardless of what we name them. The variables that contain strings or text are string or text types, regardless of what we name them. So a type system is a set of rules a compiler, interpreter, or runtime environment uses to help us avoid associating the wrong kind of data with a variable or a function or whatever. Each variable or function or whatever is meant to represent some kind of information, a type of information. If we associate the variable or function or whatever with a different kind of information, it's usually a mistake. Type systems are meant to help us avoid these mistakes. Compiled languages perform some amount of type checking during compilation. In the three examples, two of the languages require us to state the type of a variable when we declare the variable. If we try to use one of those variables in a way that's inconsistent with the declared type of the variable, the compiler should fail the compilation and issue a message that helps us understand what we did wrong. This is called static type checking, and languages that work this way are said to be statically typed. The other language in our examples, Ruby, doesn't require us to declare the type of variables. In fact, there isn't any syntax to do so. Instead, the interpreter determines the type of the variable based on the value we assign to it. In this case, the variable named "this is a string" is assigned the number 15, so Ruby considers the variable to be a numerical type. The variable named "this is an integer" is assigned a string, so Ruby considers it to be a string type. Cobbie's question today is whether Cobol is type-safe. The answer to that question depends on what actually happens when we make this kind of mistake. Does the compiler stop the compilation? Does the interpreter or runtime environment raise a runtime error? If so, then the language is relatively type-safe. If not, then it isn't. Type-safe isn't a binary answer. It's a spectrum. Some languages might be relatively more type-safe than others. Some people refer to that characteristic as the strength of the type system. Some languages are considered to have strong type systems. The strength of the type system is orthogonal to whether it performs type checking at compile time or runtime, or both. Let's look at a dynamically typed language, JavaScript. When we attempt to perform arithmetic with a string value, the interpreter assumes we intend to append a string 5 to the end of the value Charlie. It does not recognize this as a type error. Instead, it coerces the value 5 from number to string. JavaScript is dynamically typed with a weak type system. This is not necessarily bad, it's just the way the language works. It makes some kinds of programming easier, but at the cost of risking type errors that aren't caught. Here's what happens when we try to do arithmetic with the Ruby variable, this is an int, after we assigned a string value to it. Ruby considers it a string type because of the value we assigned to it. It doesn't know what to do when we attempt addition. So it raises an error and stops the program before the mistake can cause any damage. Ruby is dynamically typed with a strong type system. Let's try the same thing in Java. Java is statically typed and performs type checking during compilation. It will not allow us to compile a program in which we perform arithmetic with a string value. Java is statically typed with a strong type system. Now let's do the same thing again in COBOL. We have a data item defined with picture X. That tells the compiler we intend this data item to contain alphanumeric values. When we attempt to perform arithmetic using this item, the compiler stops the compilation. So COBOL is statically typed, but is it type safe? Let's try a few experiments to find out. The other languages we've looked at are supported on many different platforms. Something they have in common is that they behave consistently on all platforms. COBOL also runs on many different platforms, but for historical reasons, different implementations behave differently. So we want to try a few different compilers and platforms. We'll try a couple of simple programs with 3 different compilers running in 3 different environments and see how they behave. We'll use IBM Enterprise COBOL on ZOS, GNU COBOL on Linux, and the Z COBOL compiler from the Z390 Portable Assembler and Emulator project running on Microsoft Windows. There are quite a lot of specifications that are possible in a picture clause, and a lot of different variations in the usage clause too. So we'll just choose a couple as a baseline experiment. We'll try picture A, which, according to the documentation, allows uppercase and lowercase Latin letters plus the space character. And we'll also try a picture 9 field, which the documentation says allows decimal digits. We'll just summarize the results on slides rather than making you watch all the step-by-step work. On this slide we see the results for IBM Enterprise COBOL on ZOS. The compiler accepted moving AB to the picture A field, which is fine, but it also accepted moving $% to the A field, which according to the documentation it really shouldn't allow that. It also allowed a character representation of 42 to be moved into the A field, and according to the documentation that should not be allowed. It did allow a numeric 42 to be moved to the picture 9 field, which is fine, and it did stop the compilation when we tried to move AB to the picture 9 field, so that was correct. GNU COBOL on Linux performed a little worse than the IBM COBOL on compile time type checking. It did allow the AB into the A field as it should, and the 42 into the 9 field as it should, but it also allowed $% and 42 into the picture A field. It also somehow compiled with moving character AB to the picture 9 field. That was a little surprising to me. The Z390 compiler also behaved about like the GNU compiler did, except that in the last case, moving AB to picture 9, when it executed that, it appeared to treat that field as a display numeric field, ignoring the high-level nibble of each byte and treating the low-order nibble of each byte as a decimal digit. So that's interesting behavior. An interesting characteristic of COBOL is you can overwrite numerical data into memory at runtime by moving non-numeric data to a group item that encompasses numeric fields. So we tried that here with 3 different numeric formats. COBOL supports quite a few numeric formats, but we thought these 3 would be representative. So here is the result of IBM Enterprise COBOL on z/OS doing arithmetic against these numeric fields with no errors. And here's the result after we move double trouble to the group level item, and that overlays all 3 numeric fields with non-numeric data. And you can see that for the binary field, usage comp, the compiler just gives you the wrong answer, and the same for the native binary field, the comp5 field. And this is just because all bit patterns are valid numbers for binary fields. So there's no way that COBOL can check this at runtime to see if you have a valid value in the field. But for the packed decimal field, the system noticed that the data was in the wrong format and it threw an exception. So this prevents the error from causing any further damage in the application. So that's good. So here's GNU Linux, unsurprisingly handling arithmetic with numeric data correctly. But look what happens when we move double trouble to the group level item. It just delivers the wrong answer for everything. It doesn't see that the packed decimal data is in the wrong format. And the reason for that is this compiler converts the COBOL source into C and then uses a platform-specific C compiler to convert the result into object code. So by the time this runs on a Linux platform, say on an AMD 64 architecture, there is no such thing as packed decimal data. It's all binary. So all 3 of these formats have the same problem. There's no way to tell at runtime that the data is incorrect. And here is the Z390 emulator, Z-COBOL compiler, handling numeric addition correctly. And this time it's interesting that it does throw an exception when the packed decimal field does not contain packed decimal data. But this is running on Windows, on an AMD 64 processor. So how is it recognizing packed decimal data? Well, the reason is this project emulates the System390 instruction set, and it has an assembler that's pretty accurately mimics the behavior of the assembler on System390. And the way this compiler works is it converts COBOL source into assembler macros, and then those run through the assembler. And so it's imitating the instruction set, including the packed decimal instructions. So the behavior is very consistent with the enterprise COBOL behavior. So with all this in mind, I would say COBOL is reasonably type safe. It does a pretty good job of compile time, static type checking, but it does miss a few things, and the things that it misses may depend on which compiler you're running, which version of it you're running, what compiler options you've set, what platform it's running on, because it's not as consistent as languages like Ruby and Python and Java. When it comes to runtime type checking, COBOL itself doesn't do that because the compilers generate object code, or they generate another source code that gets converted into object code, so it's not playing when it comes to runtime. But sometimes the runtime environment does catch things. In particular, on the mainframe, it catches those data exceptions, or when the packed decimal data is not correct, and on the Z390 emulator project, it behaves the same way. So I hope that answers Cobbie's question about type safety in COBOL, and maybe it answers your question too. So we'll see you next time.